welcome. In this lecture, this is where I'm going to try to give you a little bit of intuition about how, like, what's going on with integration, so that hopefully by the end of it, you'll actually be like, yeah, that makes sense. I actually kind of feel that a little bit, as well as how you would do this with a more general circumstance, not how you would compute it, but how you would set up an integral. Okay, so here's, I said the word setup, and I'm going to use it in an entirely different way. This is the setup for the example we're going to kind of look at to help build intuition. So, setup. Okay, so suppose we have that, and so the way that we're going to kind of write this, don't get intimidated, please. So we're going to have, I'm going to write dp dt equals 4. Okay, so what does that mean when I write something like that? It means that the position is increasing at a rate. So this just means that the position is increasing at a rate of 4 meters per second. So this is meters per second, i.e. velocity equals 4 meters per second. So i.e. velocity equals 4 meters, I'll fully write this out at least once, per second. Okay? Okay. The first thing I gave you was a rate of change. It's the rate at which the position is increasing with respect to time, or in seconds. This is the same thing as the velocity. So the rate the position is increasing is the velocity. And then we're going to be considering, oops, to my hand. We're going to be considering so the time interval So this is going to be the time interval 1, 6. Okay, and this is again in seconds. Okay, so this is kind of our setup. This is what we know is going on. So then how would you figure out the change in position from velocity? So change in position from velocity. Okay, well, in a circumstance like this, where this is just always the same, it's always 4 meters per second, it's not varying. Okay, so in a circumstance like this, our change in position is going to equal, we're going to take this here, so we're going to take this velocity, dp dt, and think about this for a minute. If you're driving and you want to know how far you're going to go over a period of time, and you're driving at a steady rate, I don't know whether you prefer kilometers or miles, but we'll say we're in miles per hour. If you're going 60 miles per hour and you're doing that for 3 hours, how do you figure out how far you've probably gone? You multiply 60 by 3, right? Okay, so you multiply your velocity or your speed by the time. Okay, so what do we get here? We're going to get 4, right? Because that was our velocity, what we said it was going to be. The time here, I mean the length of this interval, so that's 6 minus 1 equals 5. Okay, so this is, that time is going to be 6 minus 1, so that's 5. So what does that output for me? So what that's going to output for me is going to be 20. Okay, and if we were in this circumstance where we're in meters per second, this should be in seconds, this should be in meters per second, and so you would get out that this is actually in meters. Okay? Now, I'm going to draw the picture of this, and the reason I want for you to have in your mind this picture is that a lot of times people will talk about integration, giving you the area under a curve. And you're going to see this here. Okay, you're going to kind of see how this switches into a geometric, having a geometric meaning. Why is that important? Because sometimes people give you things as graphs and things like that, and you kind of need to be able to move in between looking at functions and formulas and graphs and images. Okay, so here we go. We have our velocity is at 4, so here we go. So this is velocity. So this is going to be from, this is my velocity is going to equal, and this is just a constant function, which means it ends up being flat, so my velocity is going to equal 4 meters per second, okay? And then this axis here, okay? So this is t seconds, so this is time t, and in this circumstance it's in seconds. Notice how I'm nicely labeling my axes. It's a kindness to the world, okay? This could be, so this is the graph of this. This here, you could think of this as actually, this is velocity, is that axis, okay? Now I'm on the interval, so remember that this is a t interval, so I mark it on here. So I go from 1 to 6, and that distance there we know is 5. And so what I'm actually looking at, what did I just compute over here, is this area, right? Because if I take, how do I compute this area, right? So this area is going to equal width times height, so 5 times 4, right? Because this is at height 4, always, this tells me that this is 4. So I have 5 times 4, so the area equals 5 times 4 equals 20, and then that's this area all throughout here. Okay, now what do I do if, so this is a constant function, it's always the same, the output's always the same no matter what my input is. So what if it's not? Okay, so more tricky. Okay, so if that velocity, which was 4 there, so if the velocity isn't constant, right, so isn't a constant function, okay, we would use, okay, so we would need to use the integral, so we would need to use the integral okay, so what is this integral? We write this kind of funny s thing, and then we have our intervals from 1 to 6, so we put those as what we call the bounds. So we put 1 on the bottom and 6 here. That tells me I'm integrating over this interval. What am I integrating? I'm really integrating the velocity, okay? And then, because I'm looking at velocity as varying over time, and this is an interval in time, I write a nice dt here, okay? And this would tell me, so we would take this integral to find, maybe I'm going to kind of box this so that you can kind of see. I'm going to take that particular integral, and what it's going to give me is going to find the change in position to find the change in position okay, from time t equals 1 second. So from time t equals 1 second to time, so to, having a collision of writing, but that's easily fixed. Okay, so to time t equals 6 seconds. Okay? So, what do we do here? We used kind of first off, we know that the integration is going to take us from a rate of change to a change of quantity. And our favorite example being going from the velocity to a change in position. So we start out with a steady velocity of 4. Why do we do that? Because we have intuition as to how to deal with steady velocities because of driving or bicycling or walking. And so we're going to do that so we're going to go at a rate of 4 during this time interval, so for 5 seconds. How would you figure out how to compute that change in position? You would just multiply your rate by your time, and that would give you 20 meters, which is the same thing as if I graphed the velocity. Then what would end up happening, so this is the velocity, this is just the graph of the velocity function. It never changes, it's always 4 because it's 4 at every point in time. And so how would I compute this? Well, I'm actually looking at the area under this curve on this interval. It's the same thing as integration always gives you. And so I multiply the length of this interval times that height, and that gives me that area there. Okay, this is the very special circumstance because the velocity is constant. So what if instead I wanted to look where I have a velocity function? I know what the velocity is at each point in time. Then I can stick it into an integral where my bounds come from the 1 and 6, which are the bounds of the interval that I'm going to integrate over. And this would actually give me the change in position as I went from time t equals 1 to time t equals 6. Okay, so I hope that at least gives you some idea of what an integral is and how to at least set up an integral and why it's not the strangest thing in the world. So I hope that made a little sense. Makes you feel a little bit more comfortable with these things, and I will see you in the next lecture.